So picture this. You have a friend who is like an absolute genius,
Okay.
right? Like they've read every book, they can solve complex equations in their head, they know the history of the world inside and out. But, and here is the catch, you take this genius friend, you drop them into a pitch black kitchen they have never been in before, and you just say, hey, make me a sandwich.
Oh, man. That would be a disaster.
Right. What happens? They stumble around, they trip over a chair, they try to put a slice of bread into like what turns out to be a blender,
Yeah.
and eventually they just get stuck in a corner repeating the exact same mistake over and over. I mean, for all that brain power, they are completely helpless.
That is, I mean, it's a phenomenal visual.
Yeah,
Because it captures the exact paradox we're seeing right now at the absolute frontier of artificial intelligence.
exactly.
We have these massive language models that can, write code or synthesize legal documents in literally seconds.
Yeah.
Yet the moment you drop them into a novel, interactive virtual environment and ask them to complete a multi-step task, their reasoning just completely falls apart.
And that is exactly the mission for today's deep dive. We are exploring a state-of-the-art research paper that introduces a massive, I mean really massive, leap in how AI agents reason. It's called the Map Then Act paradigm, or MAP.
MAP.
And for you listening, whether you build AI tools or you just use them every day, this is fundamental. We're going to unpack exactly why today's AI hits a wall in new environments, how researchers are actually borrowing from animal psychology to fix it, and this is the crazy part. Why teaching an AI to systematically just look around first is completely destroying the old strategy of trying to memorize solutions.
Yeah, it really is destroying it because the foundation of this entire paper rests on diagnosing a critical flaw. And they call this the epistemic bottleneck.
The epistemic bottleneck.
Right. And to understand this bottleneck, we really have to look at the current gold standard for AI agents, which is the goal-conditioned stepwise planning framework,
Right, right.
which is a mouthful. But if you've used an AI agent recently, it was likely running on a prompting strategy like React or chain of thought.
Yeah, I use React agents all the time, actually. It's great for isolated logic puzzles or coding because, the AI gets a goal, it generates a thought token about what to do next, takes an action, observes the result, and then basically loops back to think again.
Exactly.
But the moment the environment pushes back or like if there are hidden rules, React essentially just blindfolds the AI.
Because it creates what researchers call a temporal inversion.
A temporal inversion.
Yeah, so the AI is operating on delayed environmental perception. It is trying to solve the specific task while, at the exact same time, trying to figure out the fundamental physics and rules of the environment through trial and error.
Oh, I see.
It doesn't actually know the constraints of the world until it literally crashes into them. And because it's acting blindly like that, it hits that epistemic bottleneck, trapping the agent in one of two failure loops.
Let's anchor that for a second. It's kind of like being handed a complex IKEA furniture manual and starting to screw pieces together before you've even checked if you have all the parts.
Yes,
Yeah.
exactly.
Or, if you even own an Allen wrench, you are acting to understand rather than understanding to act.
That is a perfect way to put it.
And so those two failure loops make perfect sense in that context. The first one they talk about is goal drift, where the AI gets distracted by something that seems locally plausible, but it ruins the overall goal, like screwing the wrong table legs together just because they happen to fit in the moment.
Precisely. And the second loop is redundant trial and error. This is where the AI repeatedly attempts actions that violate the hidden rules of the environment, basically just hoping for a different result.
Like trying to open a locked door 50 times.
Exactly. Now, the tech industry's default reflex to these kinds of failures is just, well, scale it up, right?
Throw more compute at it.
Exactly. Add more parameters, increase the context window, throw massive compute at it. But the paper points out that scaling up doesn't fix this. It just makes the AI fail faster.
Wait, really? Why wouldn't more brainpower fix it?
Well, they reference Judea Pearl's do calculus to explain why this is a paradigm-level flaw, not just a compute issue.
Do calculus. Okay, that is the mathematics of cause and effect, right?
Yeah.
But how does that apply to a language model trying to, navigate a digital kitchen?
It comes down to the fundamental difference between observational data and interventional data.
Okay.
See, language models are trained on massive amounts of observational data. They learn to predict the next token based on a completely static history of text on the internet.
Right, they just read a lot.
Right.
Right.
But observational data alone cannot uncover the interventional rules of a new environment. You cannot learn how a unique closed system reacts to your specific actions just by correlating past data from the open internet.
Because the internet doesn't know about this specific kitchen.
Exactly. You actually have to intervene. You have to actively probe the environment, change its state, and literally map the causality yourself.
Wow. Okay, so since throwing raw computing power at the problem doesn't solve this causality bottleneck, the researchers actually had to look entirely outside of computer science.
He did, yeah.
They went to biology and psychology to figure out how living organisms handle unfamiliar environments.
Yeah, and they drew heavily on two foundational theories here. First is Gibson's affordance theory.
Okay, what's that?
This suggests that intelligent biological organisms don't just figure out rules by failing repeatedly. Like when you walk into a room, you look at the spatial layout and immediately perceive action affordances.
Affordances, like what an object affords me to do.
Yes. You see a handle and you instantly know a door can be pulled. You see a flat surface and you know an object can be placed there. You perceive the potential for action through observation.
You don't have to walk up to the flat surface and drop something to test if gravity works there.
Exactly.
And the second biological inspiration they looked at is Tolman's cognitive map theory, which showed that organisms, like rats in a maze, they don't just navigate by simple stimulus response memorization. Right.
They don't just learn turn left for cheese. They actually actively explore to build a structured internal mental map of the entire space.
Right. And the researchers took those two biological concepts and used them to completely flip the standard AI prompting architecture on its head.
Which is wild.
Instead of the famous prompt we all know, let's think step by step.
Right.
The new paradigm is essentially, let's look around first.
Okay, but hold on. If we tell the AI to just look around and act like a scout, what stops it from mapping the environment infinitely?
Ah, that is the big question.
Because I know people who get stuck in Skyrim just reading books in the virtual library for like hundreds of hours instead of actually completing the quest.
Yeah, we all know that person.
How does the AI know it's time to actually stop exploring and, make the sandwich?
That infinite loop is a massive risk when you grant an agent autonomy. So to solve it, the paper proposes a mathematical mechanism called the dual convergence stopping criterion.
Dual convergence stopping criterion. Yes. So during the scouting phase, the AI isn't just mindlessly wandering. It's actually being evaluated by a strict scoring system operating in the background. And it tracks two specific metrics.
Okay.
The first is knowledge increment. The system calculates the delta of new rules or objects the AI is discovering, like, is it still logging new constraints? Did it just find out a specific cabinet is locked?
Got it. And the second metric?
State novelty. This tracks the spatial nodes. Basically, is the agent seeing new areas of the map it hasn't visited before.
Okay, so new knowledge and new spaces.
Exactly. And the genius of this dual convergence mechanism is that the AI is only allowed to switch from the exploration phase to the execution phase when both of those metrics hit a delta of 0 over a set number of turns.
Oh, wow. Meaning it is no longer logging new rules, and D, it is no longer entering new spatial nodes.
Yes.
Because if you only track new rooms, it might stop exploring while there are still, like, unopened drawers to check in the current room. But if you only track new items, it might hyper-focus on the kitchen and never realize there's an entire living room.
Exactly. Requiring both to hit 0 mathematically guarantees a comprehensive understanding of the environment.
That is so smart. Which brings us to the actual mechanics under the hood. The map then act framework operates in 3 distinct stages, and it fundamentally changes how the AI stores information in its context window.
It really does.
Stage 1 is cross-tasked global exploration. So before the AI is even given its actual goal, it acts as a focus analyzer. Its job is to figure out the universal physics and syntax of the world.
Like learning that you can only hold one object at a time, or figuring out the exact API syntax required to open a container in a specific software environment.
Right. And it distills all of this into a specific data structure called global knowledge, or KG.
KG, yes.
And this isn't just like a vague memory. It's a structured text block, often formatted like a JSON file, outlining the universal invariance of the world. It explicitly lists out constraints, formatting rules, and physics.
Right. And then comes stage 2, which is task-specific cognitive mapping.
Okay.
So now the AI knows the underlying physics from KG. It goes into the specific environment to explore the layout. It maps out the spatial nodes and tests those object action affordances we talked about earlier.
Like what actually happens when I pull this specific lever?
Exactly.
Yeah.
And just like stage 1, stage 2 outputs a concrete data structure. It builds a cognitive map, or MT.
MT.
Right. And in a text-based LLM, this isn't a fancy 3D graphic. It is a graph structure represented purely in text, where nodes are locations and edges are paths. State variables are tracked explicitly, like logging. Cabinet 1 equals closed contains equals unknown.
Wow. And then finally, we hit stage 3, knowledge-augmented execution. The AI finally receives its specific goal, say making a sandwich. But instead of guessing, it queries the global knowledge, KG, and the cognitive map, MT, that it just built. And then it executes the task flawlessly. So, just to recap, stage 1 is learning that gravity exists and how door handles work. Stage 2 is walking through the unfamiliar house to map out where the kitchen is and what's inside the fridge.
Yep.
And stage 3 is actually getting the goal, walking straight to the fridge, and making the sandwich.
The explicit separation of those stages is the secret sauce to the whole framework.
But practically speaking, for anyone deploying these models, doesn't this use a massive amount of computing power? I mean, you are paying for the AI to wander around a virtual space, opening doors and logging variables before it even attempts the real task. The token cost must be astronomical.
You would think so, right? But the paper's data reveals the exact opposite.
Really?
It actually costs the same or frequently fewer tokens and interaction turns to use this paradigm. The researchers actually coined the term epistemic efficiency to describe this.
Okay, how does front-loading all that exploration actually reduce the overall token cost?
Because the cognitive map fundamentally compresses the prompt context.
Oh, I see.
Think about it. Without the map, the old React models waste thousands of tokens stuck in those redundant trial and error loops. They try an impossible action, the environment generates an error message, the LLM ingests that error, hallucinates a slightly different impossible action, gets another error.
This is burning tokens.
Exactly.
Yeah.
MAP eliminates all of that hallucination. It spends a defined budget of tokens upfront to build the KG and MT structures. Then, during stage 3, the agent just references those compressed data structures and executes the task with laser precision.
Drastically reducing the total number of interaction turns.
Yes.
Okay, the theory is elegant, and the math for epistemic efficiency makes sense. But academic theory often falls apart in practice. When they actually put this MAP framework up against frontier models in rigorous benchmarks, did the efficiency hold up?
The results across models like Qwen 3, GPT-4o, and Claude are they're genuinely staggering. Let's look at the ALF World Benchmark, which basically simulates complex household tasks.
Okay.
The paper details a specific test where the AI is tasked with putting a hot cup in a cabinet.
Right. And under the old React paradigm, the AI receives the goal and just starts moving based on next token prediction. It sees a mug on the counter. Its internal weights associate mug with cup, so it grabs the mug.
Natural.
It walks over to the microwave and generates a command to heat the object, but it forgets to actually place the mug inside the microwave first.
Right, so the environment returns an error. Object not in receptacle. But because the React agent doesn't possess a global knowledge structure defining the physics of microwaves, it doesn't even understand the error.
It just tries variations of the heat command?
Yes. It gets stuck in a loop and fails after 37 painful steps.
37 steps of just holding a mug in front of a microwave.
Exactly.
But when they apply the MAP framework, the AI scouts first. It builds its empty graph. When it finally receives the goal, it queries its map and realizes that the mug on the counter is just a mug. The target item, specifically labeled cup, is located on a different counter entirely.
Yeah.
The agent walks directly to the correct cup, picks it up, opens the microwave, places the cup inside, heats it, takes it out, and puts it in the cabinet. It executes perfectly in 7 steps. That is an 81% efficiency boost.
An 81% boost. And we see that exact same dominance in TextCraft, which is a text-based Minecraft simulator.
Oh, I love Minecraft.
Well, under React, the AI tries to craft an item by blindly guessing ingredient names from its pre-training data, asking for things like stone or cobblestone. The environment rejects it, and the AI fails after 40 steps.
Classic. But with MAP, it uses stage 1 to map the specific syntax of this exact environment. It learns the required item is literally coded as stone crafting materials, gathers that exact string, and wins in 10 steps.
It's incredible. But I think the most compelling evidence comes from ARC-AGI-3.
Okay, what is that?
This is essentially the ultimate test for fluid intelligence. The AI is dropped into an abstract, grid-based game environment. It is given 0 explicit rules. It doesn't even know what the win state looks like.
That sounds like a total nightmare for a language model. I mean, fluid intelligence requires adapting on the fly without relying on memorized training data.
Which is why, under React, even Claude 4.6, which is a top-tier frontier model, scores near zero. It just flails blindly.
Wow.
But wrapping Claude 4.6 in the MAP framework allowed it to solve 22 out of 25 novel games.
22 out of 25.
Yeah. In environments like the TU-93 maze or the VC-33 scrolling belt puzzle, the exploration phase allowed the AI to autonomously probe the grid, log the physics into its global knowledge, and literally deduce the underlying mechanics of games it had never seen before.
Let me throw a wrench in this, though. What if the environment is dynamic? Let's say the agent builds a perfect map, it knows where everything is, but mid-task, something changes, like I'm making a sandwich and someone moves the mayonnaise.
Right.
Does the AI's heavily structured map become totally useless? Does the system just crash because its empty variables no longer match reality?
The researchers actually anticipated that, and they designed the perturbation tests.
Oh.
So mid-task, they would invisibly alter the environment, teleporting an object the AI needed to an entirely new location. If the AI was just blindly executing a memorized sequence, it would have crashed entirely.
So what happens mechanically when it encounters that missing object under MAP?
The MAP models exhibited what they call causal adaptability.
Causal adaptability.
Yeah. When the agent arrived at the location, the environment script returned a 404-style error. The object wasn't there. But instead of looping a pickup command over and over, the MAP framework caught the error, deliberately invalidated that specific node in its cognitive map, and automatically triggered a Stage 2 scouting subroutine.
Oh, wow.
It scanned the adjacent nodes, found the moved object, updated the MT data structure, and just seamlessly resumed the task.
That dynamic updating is brilliant. And it leads to what might be the most groundbreaking part of this entire paper, because up to this point, MAP has been a prompting framework. We are basically using clever system prompts to force existing models to act like scouts. But the researchers didn't stop there. They decided to rewire a model's underlying architecture to natively think this way.
Yes. They created the MAP2K dataset. The team used massive expert models, specifically GPT-4.1 and Claude 4.5, to run the MAP framework and generate 2,000 flawless, start-to-finish trajectories across ALF World, TextCraft, and Science World.
They recorded the entire internal monologue, every hypothesis tested, every spatial node mapped, every error corrected.
Everything. And they distilled those 2,000 dense trajectories into a training dataset and used it to fine-tune a much smaller open-source model, the 4 billion parameter Quen3.
Okay.
They named the resulting model MAP4B, and its performance completely shattered traditional fine-tuning scaling laws.
Because usually we fine-tune models using behavioral cloning, right? We show them the final perfect winning sequence, no mistakes, no wandering. If MAP2K includes all the wandering around and hypothesis testing, why doesn't that confuse the 4B model into thinking that wandering is the actual goal?
That's a great point. It's because the loss function during training isn't just optimizing for the final action, it's optimizing for the process of causal reasoning. See, training an AI solely on expert execution, traces, teaches it to imitate a solution. It becomes a glorified lookup table. But training it on complete map-then-act trajectories teaches it to internalize the transition from uncertainty to certainty.
Wow.
The model's weights literally learn the cognitive architecture of exploration, map building, and knowledge retrieval.
It is basically the difference between teaching someone the route to the grocery store by making them blindly copy your left and right turns versus teaching them how to read a map of the city.
Exactly.
If there's a roadblock, the person who memorized the turns is completely lost. The person who knows how to read the map just calculates the next optimal street. The data proves that teaching an agent how to understand an environment is fundamentally more powerful than teaching it what to do.
Absolutely.
Yeah.
And that framework is why a tiny 4 billion parameter model fine-tuned on MAP2K can suddenly punch way above its weight class and outperform models 10 times its size that were only trained on traditional execution traces.
It's unbelievable. To synthesize all of this for you listening, the map-then-act paradigm is a total wake-up call for how we interact with AI. Whether you are prompting an LLM or training a brand new agent, forcing it to thoroughly define the physics and spatial layout of its environment before it acts isn't a waste of compute. Building that cognitive map is the very foundation of causal reasoning. Rushing into act before you understand the space is exactly how you get stuck in an endless loop of redundant errors.
Yeah, and I actually want to leave you with one final implication to consider here.
Okay, let's hear it.
Right now, this paper proves we can train AI to autonomously map out and deeply understand closed, unfamiliar game environments without any human intervention. But the architecture is incredibly scalable. What happens when we unleash these map-building, causality-seeking agents to start autonomously mapping the infinite, ever-changing, open-ended complexity of the internet itself?
Man. Now that is a wild thought. Suddenly, that pitch-black kitchen we started in isn't so dark anymore. The AI isn't just stumbling around blindly trying to make a sandwich. It's methodically finding the light switch, mapping the pantry, testing the appliances, and figuring out how to cook a 5-course meal.
Exactly.
Thanks for joining us for this deep dive, and as always, keep learning.